The speed ratio of Pelton wind turbine for maximum efficiency condition. So let's start the discussion how the speed ratio of Pelton wind turbine is derived for maximum efficiency. The hydraulic efficiency is defined as a ratio of Euler head and hydraulic head. So hydraulic efficiency of Pelton wind turbine is equal to bracket start U2 into CW2 minus U3 into CW3 bracket close upon HS. So you can see on x-axis it is shown as U2 by C0 and y-axis is hydraulic efficiency, and it is a maximum when U2 by C0 is half or 0.5. Similarly, in this picture you can see U2 by C2 is half when the hydraulic efficiency is maximum, because C0 and U2 is the same, because C0 is called a spotting velocity and U2 is a inlet mean uh, absolute velocity of Pelton field turbine. So hydraulic efficiency is further written as bracket start U2 into CW2 minus U3 in CW3 bracket close upon HS. So spouting velocity C0, it is a velocity which is equivalent to conversion of total hydraulic head. So you can write half into C0 square is equal to HS. So a spouting velocity C0 is equal to a square root of 2 into HS. And inlet absolute velocity, inlet mean absolute velocity C2 is equal to CV into a square root of 2 into HS. So a spouting velocity C0 is equal to inlet mean absolute velocity C2 if CV, which is a coefficient of nozzle velocity, is considered 1. Generally, this value CV is lies in 0.98 to 0.99. So if CV is equal to C2 as a special case, we can say that half into C2 square is equal to HS, because C0 and C2 are same. So we can write hydraulic efficiency is equal to bracket start U2 into CW2 minus U3 into CW3 bracket close upon half into C2 square. Refer the velocity triangle U2 by U3. So we can write hydraulic efficiency is equal to 2 into U2 bracket start CW2 minus CW3 bracket close upon C2 square. Now we need to convert CW2 and CW3 in terms of C2 and U2 and blade angle or bucket angle. Using this inlet velocity triangle, it is clear that CW2 is equal to C2, you can see here. And for CW3, that is this one, U3 minus this, which is equal to V3 sine beta 3. But U2 is equal to U3, so you can write replaces U2 for this, and V3 is equal to V2, so you can V2, but V2 is equal to, you can see here, C2 minus E2, so all together we can write CW3 is equal to U2 is written for U3 minus V3, we can write V2, and V2 is this, so we can write V3 in case of minus C2 minus U2 bracket close into sine beta 3. After replacing CW2 and CW3, we can write hydraulic efficiency 2 into U2 into, this is for CW2, so it is written as a C2 minus, for CW3 we can write this, that is U2 minus bracket start C2 minus U2 bracket close into sine beta 3 bracket close upon C2 square. Again we can write hydraulic efficiency 2 into U2 bracket start C2 minus U2 minus bracket start C2 minus U2 bracket close sine beta 3 bracket close upon C2 square. So further we can write 2 into U2 bracket start C2 minus U2 plus C2 into sine beta 3 minus U2 sine beta 3 bracket close upon C2 square. So we can write 2 into U2 bracket start 1 plus sine beta 3 in bracket close into C2 minus bracket start 1 plus sine beta 3 bracket close into U2 bracket close upon C2 square. So we can write 2 into U2 into 1 plus sine beta 3 into bracket start C2 minus U2 bracket close upon C2 square. So as C2 and beta 3 are constant and variable is only U2, so differentiate efficiency with respect to U2 and putting 0 for maximum value. So we can write delta ES upon du du2 is equal to differentiation of this. This is the final one, so we have need to differentiate this and putting is equal to 0. So on solving we can get u2 is equal to half C2. So we can write U2 by C2 is equal to half, that is 0.5, but C2 is equal to C0. So we can write U2 by C0 is equal to half or 0.5. So this is the uh, expression, or you can say derivation for speed ratio for maximum efficiency condition of Pelton wheel turbine. So I hope you will like this. Thank you. Thank you for watching.